Is there any all the homework already scored? Have you already have your score or not? Please check out. 不用关没关系，我们就让它通风好了。我们还是要保持通风。Okay. And I think I already sent some the score for the last 2 homeworks, and I already assigned of the reference for you. So I think in the last time we are talking about the IS-232 vs RS-485, and I think you already did a good job compared to the 2 different kind of the protocol. So the IS-232 is only the single mode for the point-to-point communication, but the big difference for the IS-485, it is IS-485 can connect several devices together, only use the one transmission line. Okay, so I think this is different for compared to IS-232. Okay, and for the let's go back to the last homework about the inclinometer. Okay, so for this homework, I think most of you already have a very good answer. So I will go through that. The first case you will find, because of the end of this data move with the displacement. So actually, in the practice, we should extend the borehole much deeper. Okay, so that will let you to understand. Oops. So that will let you understand that the assumption of the fixed end in the deeper depths, this is the fixed end. Should be fixed together. Okay. And in addition, for the first case, I think you can find the data is not in the sequence. I mean, without the trend, no more trend. The data shift or vibrate in the different time. So I think there will be another issue that one is that the equipment, the inclinometer itself, maybe need to be calibrated. And another reason that maybe the borehole with the pipe, ABS pipe inside, the ABS pipe is not so fixed with the surrounding soil. Okay, so that there will be another reason for this kind of the vibration. Okay, and for the case 2, I think because this is the deep excavation. Oh, I think this is too noise. Why every time? I don't know why. Okay. For the case 2, I think because it's a deep excavation, so this is maybe installation inside of the sheet pile. So this is maybe the original sheet pile, the shape of the sheet pile. So after the construction, we will have the earth pressure, lateral earth pressure. So I would like to say, if you already learn basics of the earth pressure, you will know that they will have this kind of the shape of the pressure. So we will have this kind of the displacement with the time. So this is a very normal situation, okay, during deep construction, okay. So in the case 3, because I say we already times the scale of the measurement, so you can find the data shift in the different depths. Okay, so this is because of if we have a borehole and have ABS. Let us. Okay, so this is the ABS pipe. But the gap between the ABS pipe and the borehole, sometimes in the maybe 10 or 20 years ago, we used the sand for the backfill, with the sand to fill up the gap. But however, sometimes you can find the gap between the ABS pipe and the borehole is not so constantly. Because sometimes we may have some of the swelling of the borehole. So maybe the gap will be very, very small. It means that the sand cannot pass through if we put the sand in the top. Okay. So right now we use the grout. Use the grout like the cement with the water. Okay. So for this, they will fill all the gap between the ABS pipe and the borehole. And for the sand, they will have some problem because they will have some space. And this will lead that the vibration of the ABS pipe itself. So each time when you have a measurement with the inclinometer, so the pipe will vibrate. Okay, so that will have this kind of the measurement. And addition, you can find with that the A and the B directions, but you can find the data is not so, I mean, in the same depths. In the same depths, that may be another issue for the system error. Okay, so I think I just a quick review the homework about the case 1 to case 3. Okay. Okay. So I will keep continue for the signal processing, but for the last time that you are not here, please you can find the video online. Okay. And I would like to say, if we try to convert for the summation in the last time, if we try to convert the analog signal to the digital ones, okay, so that's what we call the sampling, the procedure of the sampling. So this is just I trying to show you that the left side is the time domain. This is the time domain. Okay, and the right side is the frequency domain. Okay, so based on this, I think the first two is the analog, what we call the continuous data. Okay, and the third and the fourth one is what we call the discrete, and what we call the digital one, digital signal. Okay, so in the last time we already talked about how can you think about the relationship between the time domain and the frequency domain. For this, I would like to start for the B case because this is the most simple and can be explained. For this kind of the continuous and the periodic signal, like the pulse, repeat pulse, or the sine or the cosine signal. Okay, if you do the Fourier transform, okay, so back to this one. I think this is very easy for the understanding with this animation. You can find this is originally the signal of the triangular signal like this. Okay. Oops. Some kind of signal are like this, and this one is a pulse, repeat pulse. But if you already learned the basics of the engineering mathematics, you will know that all the signal, this kind of the continuous and the periodic signal, can be made with several signal with a different frequency, right? So for this is the lowest signal point, frequency point, okay, with the higher point, higher component of the signal, okay, and then this is the same. So each component has its own frequency, right? For this, I mean this is the lower frequency. So I have the 1 Hertz, 1 Hertz, okay. And so for the higher frequency, for this one, maybe the 3 Hertz, and so on, 5 Hertz, 7 Hertz. And combine this together, we can have the pulse signal. But this is just the limit component for the if you try to integrate with the pulse signal. Okay, so this is the sinusoidal, and this is the complex. So it's just the mirror component. Okay, so based on this idea, I think you can explain this one. So after the Fourier series, you can find we can use the several component because this is the complex. So this is the mirror. This is the mirror. So that's why we can have the continuous impulse in the frequency domain. Okay, but however, if you look at the A case, this is the continuous signal, but a periodic. I mean, only show once. Again, okay. So only one signal, not the repeat again. So for this kind of the continuous signal, we may need a very, 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 very large component of the series. For this one, maybe we need thousands, 10,000s, or 100,000 of the component to make this signal only once, show once. Again, because this is not a repeat every time, okay, with the time. So based on this idea, because we have a lot of the component in the series, so actually in the mathematics, this looks like the continuous in the frequency domain. Okay, so let's while I trying to show you the idea of the conversion between the time domain and the frequency domain signal. However, right now in our world, because there's the limited space of the hard disk, so we can just only save or store the limited length of the signal, and with the discrete sampling signal. So for this idea, okay, I would like to repeat, have a new plot for all of you. Okay. Sorry. Okay, I think. Okay. So if I have a signal like this is analog. But actually, when we try to capture the signal into the computer, so we may need some sampling. Okay, or what we use the DT. Okay, so this is the sampling interval. So maybe we use the 1 second for the sampling. So each data point have the interval of the delta t. Okay, so this is the what we call the sampling rate or sampling interval. The same. Okay, so we can use this to capture the signal. Okay, so I would like to ask all of you, if I invert this kind of the signal into the frequency domain from the time domain to the frequency domain. Okay, so maybe this is the 1 second. Oh, sorry. If I have a good, for this is the 1 second. Okay, means that maybe this is a sine with the 1 hertz frequency, right? So can you image that how fast of the sampling we need to use to capture the sine wave with the 1 hertz before you learn the Nyquist frequency theory for your straight thinking? How fast that we can capture this kind of the sine waveform or signal?
At least 2 hertz.
At
least 2 hertz.
2 hertz. Okay. So someone would say 2 hertz. Okay. Started first, maybe this one or this one. Okay. 2 hertz means that I have maybe more than 2 points in 1 second, right? Okay, so maybe I can plot like this one. Okay, and again, okay, this is another in the next second. So at least I can plot like this one because I have maybe 2 points in 1 second. Okay, so I would like to say the sampling dt, the delta t, will be very, very important if you try to capture the signal. So in the last time, let's go back to the in the last time, in the end of the class, I think we already introduced the idea of the Nyquist frequency. This is the theory that say that if you try to capture, for example, the 1 hertz signal, you may need 2 hertz of the sampling frequency. At least you can capture the basic trend of this waveform. Otherwise, there will be like this one. Okay, this is what we call the aliasing. The black one is the original signal. But however, if you have the very low sampling frequency, like this one, sample 1, sample 2, sample 3, sample 4, sample 5, sample 6. So actually, the red signal is not the original one. It has a lower frequency, okay? So if you try to recover the original signal, so make that you need the sampling frequency twice than the original one. So like this one, you need twice sampling frequency. So at least for the connection of this black point, sorry. If you try to measure so at least you can find the red line signal is much similar for the original one. So of course you will say that, Professor, of course we can use the much higher frequency, sampling frequency, to sampling the data and recover the signal, right? So can you agree that? So why not? If we can use the higher sampling frequency, so that we can recover the original shape of the signal. Yeah. Okay. But I would like to say in the end of this chapter, I will explain. That's why we cannot use so much higher frequency sampling for all monitoring. Okay. So this is the first one. I would like to say this is the what we call the time domain aliasing, because you have a lower sampling frequency for the signal. And this is the concept from the time domain. If you use the concept in the frequency domain, well, like this one, this will be the original signal and have their its own spectrum in the frequency domain. Okay, so for this signal in the left side and the right side is the frequency component of it. So right now, if I try to invert the analog signal to the digital one, so right now I have like the sampling rate. This is the T0, means that the sampling interval. Okay. And the time domain, this is in time domain. For the frequency domain, you can find here the inverse of the time interval will be your spectrum. The higher is the frequency spectrum you can use. But however, based on the Nyquist frequency theory, only half of your sampling frequency, I mean half, is from here to here, is actually you can use based on the Nyquist frequency theory. So if I transfer this analog with the T0 sampling interval, like this one, 1, 2, 3, 4, 5, 6, and so on. So actually, you can find here the frequency may have some of the overlap because of the time domain aliasing problem. Okay, because you can find here I just say based on the Nyquist frequency theory, only half of the spectrum we can use. So for the T0 and for the inverse, okay, F. And right now we only have the half, so we need to times the half. So right now we only have this spectrum. if you use this kind of the sampling frequency. So here, compared to the original spectrum, some of the higher frequency component, we cannot tell from, okay? We cannot distinguish the difference in the higher frequency component, okay? Can you understand of this? Oh, okay. So if you can accept this. So for this area, this is what we call the effect of the time domain aliasing. So if we try to understand the higher frequency component, means that we need to increase the sampling frequency, maybe twice again for this. Oh, oops, this should be the twice again. Okay, so means that I have, so I'm sorry, this should be the T, I changed to the T1. Okay, so for this, the F should be changed to the inverse of the T1, and then that will be the twice, much larger than the original spectrum. So right now, I can see here to here. But based on the Nyquist frequency, actually, the only half still we can have. But however, compared to the T0, I extend the higher frequency compared to the previous one. So right now, I can see whole the spectrum of the original one, including the higher frequency, and without the aliasing. Okay, but some of you will say, why we have the repeat the frequency spectrum? Why? Because I would like to say it's very, very easy to understand. Okay, let's go back to the this one. So I will let you understand is from the, this is a very easy for the understanding of the conversion between the digital from the time domain to the frequency domain. Okay, sorry. Okay, I just keep that. Okay, so for that, the previous. So right now, if you have a dt delta t, it means that in the frequency domain, you can have the higher is the frequency here is the inverse, right? To the depends on your sampling frequency. But however, I'd like to say this is the higher frequency you can capture from the signal. But actually, you need to divide it to the two. Only half frequency you can use for the analysis because of the limited of the Nyquist frequency theory. Okay, so actually I just can see the half. Okay, so this is the sampling frequency. This is the Nyquist frequency. You can see. Okay, and I would like to say, I already mentioned that because in your laptop or PC, the disk space is limited, so you cannot store the infinite length of the signal. So we only can store the limited length of the signal. So next, I would like to say another issue for the time domain signal sampling. This is what we call a truncation. Oops. Okay. here you can find this is a very simple case for you for the understanding what is the effect of the truncation. For this, oops. In the left side, this is the periodic sine signal, right? But due to the limited of the PC space, because you only have maybe right now, what is the max of the disk, max space, storage space? A gigabyte, right? I'm not sure. Okay. Okay. So the only limited length of the signal we can capture. Okay. So for this case, it is very lucky because we truncate the signal from the start to the end of this sine wave. So for the inverse of the to the frequency, so I can find this is the maybe 2 hertz signal of the sine wave. But however, if I have the limited space and I have a truncation from this to this is the 2.25 cycles of the sine wave. So I just say that, let's go back to this one. Okay, I think this is the same idea. For the continuous and the periodic signal, I can find a very good component in the frequency domain. But if you have the truncation, means that I can find the signal only once in a limited length. So I need a lot of component infinite component to what? To establish of this kind of the 2.25 cycle of the signal. So that's why the truncation will be a big problem, because you can find actually the real component of this signal. Because you can find the difference of these two. Okay, and another issue that if you have the limited length of the signal for here, let's maybe we use the, I like to use the total length T, big T. So maybe you can answer me that if I have a big T, I mean the total length, the time length of this truncation signal. So what is the lowest frequency in the frequency domain of this signal? What is the lowest frequency? Can someone answer that? What is the lowest frequency if I try to convert to the frequency domain? If I already capture the T, maybe 100 seconds of this signal. Okay, I would like to say very easy again. The lowest frequency is the T inverse, big T inverse. So means that if I have the 10 seconds of the signal, means the lowest frequency is 1/10. It means that only I can see is the 0.1 hertz. I can understand. Yes. For example, if I have a 10 seconds of this signal, so actually I can only have the 0.1 hertz, the lowest frequency I can see. Okay, so let's go back to the the previous this one. Okay, maybe I need another. Sorry for that. Okay, so let again remind you again. If I have the signal dt, so what is the highest frequency I can see based on the Nyquist frequency? Originally, the length will extend to the inverse of the dt, delta t. But however, just only half of the spectrum we can see based on the Nyquist frequency, right? It's just half. Sorry. Okay, so this is the higher frequency we can see. But next, if I only capture the length of this dt, this big T, so what is the lowest frequency I can see? So this is the frequency range actually from the inverse, but from the time domain to the frequency domain we can use. So again, this is the depends on your sampling frequency, but only half, I would like to say only half you can see. And the lowest frequency is depends on your truncation length, the length of the truncation. Okay. And I would like to say, because right now we are all the signal here we are talking about is the discrete signal, not the analog signal anymore, because right now this is the discrete, point by point. So here you can find in the time domain, we have a point. But actually in the frequency domain, we have only point data. Okay, so in the frequency domain, what is the point between? If I have, for example, actually, I found this spectrum is like this one. Okay, but only half. But after this one will be the time aliasing. Here, this is a time aliasing area. And after that, repeat again. Okay, so that's why in the frequency domain, you can find the component will repeat and repeat again, because this is just the sampling limitation. Okay, but however, in the frequency domain, I only have this one data. And for each data, the spacing, right now, this is not the, I would like not to say the interval. This is the hertz. So each hertz between the data point in the frequency domain depends on your lowest frequency. Depends on your lowest frequency. So for that, if I have a 10 second of the signal length, so right now I have maybe 0.1 hertz in the lowest frequency. And in the frequency domain, for each data point, this is an increment of the 0.1 hertz. Increment is 0.1. until to the dt. For example, right now dt, if I use the 0.1 second, so what is the highest right now? Maybe this is a 10 hertz, but actually I just only can see the 5 hertz signal because of the Nyquist frequency series. Okay, so I think if you can understand the basics of this, and the next I would like to use the MATLAB case for the demonstration. Okay, so let us, if you already bring your laptop, or otherwise you can see the your classmate with a classmate for the practice. Okay. So let us to find the the example here. I already maybe put on the. So the first case, please open that the time aliasing example. You already download that from the. You can download that from the double E. Anyone not can find the example?对，在教材里面，对。大家先开起来哈，先开起来。Please open that. If you not already download it, please download it from the E-class platform. Okay, so if you already open that, please, you can find here. I updated this in 2016. Okay, started, but I already have some modification, right? Okay, and I would like to explain some of the parameter first. Okay, so the first Fs right now is the sampling frequency. Sampling frequency means that the inverse of your dt, inverse of your dt. Because I would like to say I use this for the better simulation of the signal. And here F1, F2, F3, it means that the frequency component of the signal. So right now I use the 3 component with the 300 hertz, 200 hertz, and the 204 hertz. For the example. Okay, is there any problem? 有没有人没办法下载的？怎么了？好。And then, so later I will explain these 3 components, okay? Because I try to build a 3 signal and combine together. And these three signals has their own frequency, 300, 200, and 204. Okay. So and the next, the time duration is the 1 second. 1 second. You can change by yourself. Okay. So the next is the data point. The data point, because this is depends on your duration and the sampling frequency. So means that if you have a 1 second of the duration with the 1000 of the sampling frequency, means that I have a 1000 point in this signal. And the next, I would like to use, this is the option of the downsampling. Okay, you can change later. And for the here, from the line 13 to the line 18, this is the example from the time and the frequency domain generation. And okay, so the first one, dt, the same is the frequency, the inverse of the frequency. So the frequency, sampling frequency, also the inverse of the dt. And I try to build a length, a series of the lengths here. Okay, so if you already know that the operation of the MATLAB, I think you can understand this is the creation of one array from the 0 to the dt times the data length minus 1, and the spacing is dt, just I say. Okay. So, okay, let me show you later. And for the DT2 means that I use the downsampling, Okay, right now, the original sampling frequency is 1000. So if I use the downsampling to the half, means that I try to compare another sampling frequency is the 5 Hertz or 500 Hertz. One is the 1000. The other one is the 500. So I try to compare these two sampling frequency. Okay, and this is also the length to create in the frequency domain in the 17 to the 18 and for the 21, I try to use the very simple idea. Just you can find the Y1 is the first 300 F1 Hertz frequency, and the Y2 is the 200 frequency Hertz, and the Y3 is 204 Hertz. So I combine these three together and use the FFT. Very simple in the MATLAB to transfer from the time domain to the frequency domain. Use the FFT command. Okay. So the Y1 is the original one, but the Y2 is just the half sampling data point. Okay, and the next is just the outcome of the result, and I try to plot. So if you already understand, it's a very easy example. So if you can run, please run by yourself. Run the program. Okay. Can you run the program? You should find the figure like this one. We have 3 figures. Is there any problem? No. Okay. If you have any problem, please let me know. Okay. So please look at the blue one in the first figures. The blue one is the original data that combine the 3 frequency signal, 300, 200, and 204. Okay, the blue one. So this is like a very dense plot. Okay, and for the red point, what is that? It means that only half sample The blue one is used the 1000 hertz for the sampling, but the red point is mean that you used only 5 hertz for the sampling. So you can find actually the red point is just only half of the blue one, because here you can find right now the total length is the 1 second. So means that in here there's a 1000 point of the blue data, but only 500 points of the red one. Okay, so this is the first. I try to let you understand. And please go to the figure 2. Okay, figure 2. So you can just find this is a 2 component in the frequency domain. One is the magnitude, and the lower part is the phase. So let us ignore the phase first, okay? Because if you try to explain the phase, you can use the mathematics equation, okay? In the frequency domain, you can change the amplitude and also the phase. But we try to look at the magnitude. In here, you can find actually we can distinguish the 3 point from the 100, 300, 200, and the 204. And you can find here, actually, I just plot the frequency domain up to the 500 hertz, because this is the first case. If I use the 1000 hertz for the sampling, so what is the Nyquist frequency? I can see if I use the 1000, 500. Okay, so right now I think I supposedly all of you understand this. So here I just plot the half of the sampling frequency, on the half of the sampling frequency, right? But however, you can find the data, this data, the figure 1 data only have a 3 component, 300, 200, and 204. But however, if you look at the figure 3, this is the figure 3. Right now, this is the result of the 500 hertz. So can you tell me if my sampling frequency is 500 hertz, so what is the Nyquist frequency? 250. So that's why I just plotted to the 250. So based on this result, I just only can see the 200, 204, but the 300 component I can see because my limitation is up to the 250 hertz. So compared to this one, the left side is the 1000 sampling hertz. The right side is the 500 sampling hertz. So this is the comparison, but with the higher and the lower sampling frequency. And this is the effect of the time domain aliasing. So if you try to compare much more, you can change the downsampling ratio here. Right now, I use the downsampling for the 2, means that from the 1000 to the 500 sampling hertz. But if you use the 3, downsampling to the level 3, 3 means that 1000 divided 3. So I just only have maybe 333 sampling hertz. Okay, if you have a 4, means that I only have 250 50 hertz of the sampling. Okay, so you can change it by yourself. or you can change it by yourself in here, downsampling ratio. Or you can change the sampling frequency by yourself, or even the component. You can change the 300, 200, and 204. Depends on your favorite, okay? Here, is there any problem? So I would like to open the second example. Please open the time truncation example. Okay, I think all the program much similar with the previous one. Okay, but I would like to say here, I would like to control the window length with the truncation ratio, truncation the ratio. So here, this example, original one, and with only maybe the 1/16 length. Okay, so if you can run program here. Okay, I would like to say, please see the result. This is just only the 1/16. Of course, this is the very strange case. Here you can find the blue one is the original length of the signal. But if I have a truncation, red is the result of the truncation. So here you can find, if I transfer the signal of the red and the blue to the frequency domain, what happened? Very peak component. I can tell this is a two component, 100 and 110. But however, if you have a limited signal like this one, the red part for the signal processing, there will be like this one, the red one. Means that also this signal have a 2-point component, 100 and 110. But with the limited sampling length, I mean the truncation effect, these two components is not easy to distinguish. I can tell from, is there only one component or there's two components? With the case that these two components is very, very close together. Okay, but if I extend that, if I not use so much, let you see, it's just only the half. Okay, so for this case, I use the rate only the half length of the blue one. You can change here in the line 12 by yourself. Line 12 by yourself. You can find for this case, it is easy, still easy can distinguish the two components from the 100 and the 110. Okay, let us to keep continue. If I use the lower, maybe the quarter length. Okay, you can find here, this is the quarter length. A little bit difference between these two components, but still can find the difference of these two components. But if I extend to the A, 1/8, only 1/8 of the original component, you can find the difference between these two components is not so easy to distinguish if I have only one S. So that is to the 16 originally the case. So for this case, you cannot so I would like to remind again, because this is very important. Because you only have the dt, very small dt, very small, very small big T. Big T means that I have a very large of the inverse of the big T. So in the frequency domain, the data, the sampling frequency between the data and the data in the frequency domain will become larger. Means that the resolution in the frequency domain decrease because of the small big T. You can find that. Sorry. If you have a small big T, means that you have a lower resolution in the frequency domain. And what is that? So you cannot distinguish, for the example, 100 and 110, because your resolution is much larger than the 10 Hertz. So you cannot tell from the 100 and the 110 Hertz component because you don't have the resolution smaller than the 10 Hertz. Okay, so that's why I trying to explain that from these two figures. Okay, again, use the blue one. Okay, so I have the dt. Okay, so the higher is the frequency here, inverse of the dt, but only half I can see. This is because of the Nyquist frequency. Okay, I have the length of the big T. This is the truncation. So the lowest frequency here is the T inverse, big T inverse. And also I would like to remind you, each data point in the frequency domain is the T inverse. So the length in the time domain will control and dominate the resolution in the frequency domain. Your sampling interval in the time domain, dt, small t, will control the highest spectrum you can see. Highest spectrum you can see. Okay, so I think this is the basic conclusion for the time and the frequency inversion. So if you can understand this, means that you already understand the sampling. You already understand the sampling. So let us maybe take a 5-minute breaks. Okay.